Welcome to Selection with Sathi. Today we cover minimum spanning trees, one of the most important graph topics in data structures and algorithms. We will learn Kruskal's and Prim's algorithms with actual code on screen, understand the cut property and cycle property, and trace through complete examples. This is a high-frequency topic in GATE CSE and coding interviews. Let us begin. Let us start with MST Properties. A spanning tree of a graph connects all V vertices using exactly V-1 edges with no cycles. A minimum spanning tree is the spanning tree with the smallest total edge weight. If all edge weights are distinct, the MST is unique. An important property: if you add any non-MST edge, it creates exactly one cycle. Removing the heaviest edge from that cycle gives back the MST. These properties are the foundation for both Kruskal's and Prim's algorithms. Kruskal's algorithm takes a greedy, edge-centric approach. Look at line 2 first. Sort all edges by weight in ascending order. Lines 6 through 10 iterate through sorted edges. For each edge, check if adding it creates a cycle using union find. Line 7, find the root parents of both endpoints. Line 8, if they are in different components, no cycle, so add the edge. Lines 11 and 12, stop when we have V-1 edges. The time complexity is O of E log E for sorting, plus near-linear union find operations. Prim's algorithm takes a vertex-centric approach, growing the MST from a single source. Look at line 5, we start with vertex 0 in the min-heap with weight 0. Line 8, pop the minimum weight edge from the heap. Lines 9 and 10, if the vertex is already visited, skip it to avoid cycles. Lines 11 and 12, mark the vertex visited and add the edge weight to the total. Lines 13 through 15, push all edges from this vertex to unvisited neighbors into the heap. Time is O of E log V with a binary heap. Prim's is better than Kruskal's for dense graphs. The cut property is the theoretical foundation of MST algorithms. A cut partitions the vertices into two disjoint sets S and V-S. The edges crossing the cut have one endpoint in each set. The cut property states, the lightest edge crossing any cut must be in the MST. This is why greedy works. In Prim's, the cut is between visited and unvisited vertices. In Kruskal's, the cut is between the two components being merged. If two crossing edges have equal weight, the MST may not be unique. The cycle property is the complement of the cut property. It states, for any cycle in the graph, the heaviest edge in that cycle is not in the MST. The reasoning is simple: if that heavy edge were in the MST, we could replace it with a lighter edge from the same cycle, giving a lower total weight. This property is useful in gate questions where you need to prove that a specific edge cannot be in the MST. Together, the cut and cycle properties fully characterize which edges are in the MST.
Let us trace Kruskal's algorithm on a 5-node graph. Edges: A to B weight 4, A to C weight 1, B to C weight 3, B to D weight 2, C to D weight 5, C weight 6, D weight 7. Step 1. Sort edges. We get A to C1, B to D2, B to C3, A to B4, C to D5, CE6, DE7. Pick A to C with weight 1. No cycle. MST has one edge. Pick B to D with weight 2. Different components, no cycle. MST has 2 edges. Pick B to C with weight 3. B and C are in different components. Add it. 3 edges. Next is A to B with weight 4. But A, B, C are already connected. Adding A to B creates a cycle. Skip. Skip C to D weight 5 too, same reason. Pick C with weight 6. E is new. MST now has 4 edges, which is V minus 1. Done. Total MST weight, 1 plus 2 plus 3 plus 6 equals 12. Now let us run prims on the same graph, starting from vertex A. Initialize, heap has A with weight 0. Pop A, mark visited. Push edges A to C weight 1 and A to B weight 4 into the heap. Pop C with weight 1. Mark visited. Total is now 1. Push C to B weight 3, C to D weight 5, C weight 6. Pop B with weight 3 from the heap. Mark visited. Total is 4. Push B to D weight 2. Pop D with weight 2. Mark visited. Total is 6. Push D weight 7. Pop C with weight 6. E is not visited. Mark visited. Total is 12. All vertices visited. Prim's MST weight is also 12. Same as Kruskal's. Let us compare the two results side by side. Kruskal's selected edges, A to C weight 1, B to D weight 2, B to C weight 3, C weight 6. Prim's selected edges, A to C weight 1, B to C weight 3, B to D weight 2, C weight 6. Same edge set, same total weight of 12. This is expected because all edge weights are distinct, so the MST is unique. The key difference, Kruskal's is edge-centric and works well for sparse graphs. Prim's is vertex-centric and better for dense graphs. Kruskal's is O of E log E. Prim's with a binary heap is O of E log V. Now, an MST uniqueness question. Graph has edges A to B weight 1, A to C weight 1, B to C weight 2. Apply Kruskal's. Sorted edges are A to B 1, A to C 1, B to C 2. Pick A to B with weight 1. Then pick A to C with weight 1. We now have V minus 1 equals 2 edges. Total weight is 2. Could we get a different MST? If we pick A to C first instead of A to B, we still pick A to B next. Same edge set. B to C with weight 2 would create a cycle with A to B and A to C, so it is always excluded. The MST is unique here with weight 2. Non-uniqueness occurs when swapping equal weight edges produces a different spanning tree.
Quick exam tips. First, greedy works for MST because of the cut property. The lightest crossing edge is always safe to pick. Second, use Kruskal's with disjoint set union using path compression and union by rank. This gives near linear time for the union find operations. Third, Prim's with a min-heap is O of E log V, which is better than Kruskal's for dense graphs where E is close to V squared. Fourth, for gate problems, sort the edges, apply Kruskal's step by step, and sum the weights. Practice with 5 to 6 node graphs. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.